Good morning, everyone. My name is Uddesh Soman. I am currently a student at Ujjain Engineering College studying electrical engineering at 7th sem. Today, welcome to the AI Club. Today, we are going to see the hands-on example of BERT, how to use BERT for text classification. So, just to give a general idea, in this problem, we will use BERT, BERT that is available in TensorFlow as a TensorFlow Keras layer, and we'll use that BERT layer along with our deep learning network to classify to conduct basic binary classification. We'll conduct basic binary classification using BERT, and the data set we have here is general IMDb data set about movie reviews. So whether a movie review is positive or not negative, that we will classify using BERT. So starting first, we'll need couple of libraries. So TensorFlow text library, it has preprocessing library functions for BERT. So you'll have to install that, and also TensorFlow models. These are couple of dependencies that we require for uh, for importing our libraries. So we have installed that. Next up, we'll need the OS function. These are just for creating the directory since the data set is available online. So we can, so in order to create that hyperlink directories, we are going to use these. Otherwise, if you have data set in your Google Drive or your local machine, then you have to create the directory accordingly. Matplotlib for plotting, and this official NLP optimization. We'll use the Adam optimizer. So that is available in this library, official NLP optimization. And the main BERT they're going to use here, it is available in TensorFlow Hub. So we have imported that as well. So starting with, we'll need to get our data set. And in order to get our data set, that data set we are using today, IMDb data set, is actually available on this directory, AI Stanford edu. So from this we have copied the URL here. We get the data set. So Keras has built-in utility function get file. So it's in Keras utilities. We call this function. We have the name of the file that we are looking for. This is the name of file, our URL, and couple of settings, cache dir. So this function actually fetches your data set from this directory. We need to we create a data set directory. This function will create a directory. So there are further functions that actually take your training data from the directory and then split them into training and testing sets. So for that data set directory, and we finally create a train directory using this dataset dir, and from dataset dir we fetch the train data set. These are
So,
all built in. Yeah.
yeah. Soman, one question on this is
Yeah.
on this Google Colab Pro, the process will be exactly same or it will be different because here we are telling to install to set up the OS and all, no? So whether it will allow or
uh,
not.
uh, just few different. I am using Google Colab Pro right now, if you see. So
Oh, okay, okay. So
this code will work just fine on Google Colab. If you are using on local machine or any other cloud-based computation system, then you'll have to make few changes in code according to that.
ठीक है, ठीक है. Okay, thank you.
Yeah.
Got it.
No, it will be more or less the same code. So finally we get the training directory from the dataset directory. These are all folders, tab separated folders within this at this URL. So for that we have done that. We have done such kind of coding and we obtained the directory. This will download our data set. You see here, our data set is downloaded. And from that data set, we create our training data set, validation data set, and testing data set. So in order to create these, this is a random shuffling function. It will add some shuffling to the data set. Autotune, this autotune object is available in TensorFlow. So you can call it using tensorflow.data.autotune. Batch size, what would be the batch size of our our sample? So each batch will contain 32 number of samples in according to this example. And seed is just for holding the random state. So you can use any number, doesn't matter. Next up, we take the raw train, we create a raw train data set. We'll take all the data sets from this. So raw train data set, we call this function text data set from directory. So TensorFlow already has built-in function for these text data sets. So we'll just call that from directory. We have this directory imported, yeah, ACL IMDb train, and we provide batch size, validation split. To remember here, validation split. So what would be our validation split? We have to predefine it. So here it is 0.2, which means 80% of the data would be used for training and 20% for validation during the training process. And by passing this subset training, which means it will declare that the particular data set called here is actually training set. And we pass the seed value just to hold the random state. In order to get the classes, what are the classes available in our data set? We just call this data set object and class name. So it will fetch the class names, whatever are the classes, object classes that are available in our data set, it will fetch it. Train data set. So obviously we have to get the train data set. So
Someone,
yeah.
one question on this. Object classes means the number of columns, na? Column names.
No, object classes means whatever your target variables are. Like here we are just doing binary classification, positive and negative.
Oh, okay.
Those are the name
Achha,
of classes.
is there means before going, do we have like how exactly the data set look like so that we will have more, means we will be able to correlate more, because right now, because
Ex-
previously whatever examples which we have, na, or means just by
yeah.
header we came to, means we were able to correlate like how, what are we talking about and all. Yeah.
Hmm. No, actually, Panda. I know the for viewing the data set. I know the functions in Pandas, but I'm actually not familiar with those kind of functions in TensorFlow. But I'll give you a glimpse here
Okay.
from that data set. Actually, we can call this take method, and we have printed here.
Oh, okay. Yeah, it is there.
So,
Okay, then go ahead. Go ahead. Thank you.
so since we have declared this raw train data set as sub-training, it would take 80% of the data from our directory, and 80% of the data would end up as training data. So here we call cache. So from that raw train data dot cache dot prefetch. So it will take dot cache, take the values, and prefetch would actually add this our buffer size auto tune. So that randomization it would add to our data set. Validation data set again, we have to declare here. Here remember we have made the subset validation. So subset validation means it would be validation data set and it would take the validation split. So 20% of whatever the data we have. The function is same dot tf keras utils text dataset from directory. Again, we call this cache and prefetch on validation dataset. So now we have our training dataset as well as validation dataset. For test dataset, since we have gone, we are going through this process that we take training data make a validation split. So that end up as validation during training, and for final testing means for final testing of the model, we take a totally isolated set. So that totally isolated set is actually this test set. So it's available again. It is available at our address. This AI ACL IMDb/test. So we call the test data set from directory. We take the whole data set actually as test data set, and again cache and pre-patch. So it took all that data and it has given us the result. So for training, for the purpose of training, we have 25,000 samples. Of those 25,000 samples, 20,000 samples are being used for training, 5,000 are being used for validation. And again, for the test set, I guess it's 25,000 samples again for testing purpose, final that isolated testing. And again, I said I am not familiar with that create the whole Excel sheet type function, Excel sheet type display in TensorFlow, but we can get couple
I
of
think,
sentences.
see, someone it is like this. I think if you say import pandas is PD and
Hmm.
use same
Yeah,
Python
if we
functions, and yeah, I think it will work.
yeah if we do it with pandas, it would definitely
Yeah,
work.
just import
No.
pandas and you start work using it as you are using, as if you are using in a Jupyter notebook. Same thing will work actually, no problem.
Although I would say it's better to use TensorFlow data functions because we won't face any compatibility issues later on when we create the model because TensorFlow would adjust accordingly. It would include that data pre-processing as well. No? That's why. So it's
Okay,
better
Yeah.
to use
so
TensorFlow, but we can do pandas as well. No problem at that.
But someone and actually, what difficulty right now I am facing is because
Hmm.
before, suppose if I have a database, then there is some preview is there, na? So we
Hmm.
know like how the columns looks like and what exactly is the how the means before attempting any problem, it will be good to have a preview of the how the data
Yeah.
set looks like.
So,
So here I am
sir,
not
if
able to till now I am not able to correlate here because last time it was a Twitter and score, so it was
hmm,
we were able to correlate. But here till now I am not able to see what is there in the data set and what are we exactly trying to achieve. So if you just
hmm.
throw some light on that, no, then it will be very helpful. Yeah.
I think if you want to get the feel of how data is and
Yeah.
all that,
Yeah.
so
Yeah.
in so that is actually part of analysis. So I would say go with pandas for that case. If you want to get the feel, if you want to see the data frame and all, go with pandas. And once you are done with your analysis, so for the practical purpose, for actually creating the model file, then you go with TensorFlow. And for the purpose of showing here, we have this output, na?
Okay. 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 So what we are telling is first whatever we have learned in our earlier classes, that will be good idea to go follow all those process and then apply this, so it will
Yeah,
be more
for for
efficient.
analysis
Yeah.
purpose, go with pandas. You can do all the analysis, whatever it is required. You can do with pandas. It's easier that way. And then
Uh,
when you are finally making the model,
uh,
finally passing the data for model, then go with TensorFlow built-in library, built-in functions.
okay. Okay. ठीक है ठीक है चलेगा यार. Let us
Yeah.
proceed. Yeah.
Okay. And for visualization, here we have from training data, we just take take one. That take one is actually it will fetch the data one batch. Take one means one batch, and from that we take text batch and label batch. So from text batch and label batch, we are for here we are just printing three reviews. So we just call the print function batch numpy I. So ith number of review dot numpy would actually convert it into array because directly not give us this kind of output. We have to first convert it into NumPy array, and from that NumPy array, we'll get we
Yeah,
can
but so on, see, within the train, from the train data, we have fetched only one record, right?
one batch.
One batch of 32
Yeah,
samples,
32
right?
samples. Yes, sir.
Okay, okay. And from
And
there, we
from
have taken the first three.
yeah, okay. So we take the text batch, calling NumPy to just get the string output. It would not change our text batch. It's just temporary thing. Text batch NumPy I, and we uh, print it. So this would give us our statement. So you can see here, this is a movie review. Pandemonium is horror movie spoof that comes off more stupid than funny. Believe me, it's a big review. And taking the label. So again, label converted into NumPy batch. And from that label, if you remember, we have taken class names as well, right? In earlier process, we have fetched the class names. Where to? Yeah, class names. This part here, we fetch the class names from our data set. So we call the class name as well, and we pass our label into those class names. So you see here, for 0 class, we have this class name negative. For 1 class, we have this class name positive. So this kind of data set we have for just a basic visualization. For basic visualization purpose, we have this kind of data set. Moving on, we finally need our BERT model. So BERT, the TensorFlow BERT layer is actually comes in 2 parts. It's a pre-processing and the BERT encoder. So in the theory session, we have seen what are the encoders in BERT and what are the working of BERT, as well as the pre-processing that happens within BERT. So to do that, we'll need a preprocessor as well as encoder. So we'll need to select a BERT model. So there are multiple BERT models. The original BERT paper, that was released by authors, that from that paper there are 7 different models, and there are other models as well. This small BERT, Albert, BERT experts, Electra, and in theory session we have seen another Roberta. That's actually that's also BERT, a robustly optimized BERT. But here, for the purpose of example, we'll keep with small BERT. So this is the name of model that we are going to use, small BERT model. And you can take any model that is available here. You see this whole dictionary of models and their links. So all the model files all the pre-trained model files that we need are actually available at these links. So you can just have a name here. It will, and from this dictionary, it will take your encoder, and we have another dictionary that will take your pre-processing layer. So pre-processing layer as well as encoder are available online. You just have to know the name. You just have to select a model, and it will use it as a key and fetch the link for here. Let me just come to it. Yeah. Earlier we have declared the model name, and from these dictionaries we fetch the encoder layer. So it will get the hyperlink for encoder layer as well as hyperlink for pre-processing layer. So just to show the selected hyperlinks, we print these both, and we get selected model. We have this model selected, the small BERT, which is available at this hyperlink, and the its pre-processing layer. So pre-processing layer is available at this link. So moving on to actually get your layer, to get your layer, we call this BERT pre-processing model. Just declare our object, and from TensorFlow Hub. This is not TensorFlow. This layer is actually imported from TensorFlow Hub. From TensorFlow Hub, we call this function keras layer. It will create a keras layer out of our preprocessor. So earlier we have uh, had the link of preprocessing layer, and it will create the keras layer out of it. And to just, since these are pre-trained, you can directly use them for working. So just see here, we take that just a simple testing text. Listen, this is such an amazing movie, and this text goes through our pre-processing layer. This pre-processing layer we declared here as BERT pre-processing model, and it's a keras layer. So we pass our text into this BERT pre-processing model. The same thing that we did with Spacey, if you remember. We directly took a sentence and we passed it to the Spacey model. We got all the doc objects. Similarly, here we get the pre-processed outputs of BERT pre-processing layer. So if you want to see the keys, what are the keys that are available here? So input mask. So if you remember, there are masking. Masking happens in BERT. So for that input mask, input word IDs. So these are simple word IDs. Input type IDs. What are the type of inputs? So IDs for that, and we print all these. So from that pre-processed text, after passing through model, we get this object pre-processed text, and we call this input the thing that we want to fetch. So if we get here, what are the keys that are available? So input mask, input word IDs, and input type IDs. So these are actually the keys that are available to us to fetch. If we see the shape of input word IDs, so here we have 128 separate input word IDs in this single statement. And if you want to actually see the IDs, so here we have just called first 12 IDs. So these are first 12 IDs. These are actually, if you remember, there was this masking process and encoder system. So for that, preprocessed IDs, for masked IDs, if you remember, there was masking process. Masked LM was part of BERT. So for that, the masking process is also done. So one means it is normal, 0 means it is masked. And input type IDs. So what are the type of input? That actually is that sentence encoding. So if you have multiple sentences would be encoded separately. Since here we have only one sentence, so the whole statement is actually encoded with 0, which means each part is 0. If there were multiple sentences, we would have got 0 followed by 1 followed by 2 for as many number of sentences that we have. Since it is pre-trained, we have directly used it. Again, while creating a mod of it, we'll see how it works. Again, after that, after the pre-processing, we need encoding layer, the main BERT encoder. So earlier we have fetched the hyperlink for our small BERT that we are using, and we call the keras layer, and we get small BERT. So the pre-processed text in the previous step, we have used this pre-processing layer to convert the text. So we take that pre-processed text and we pass it to our BERT model. So we'll get BERT results. And from that BERT results, we can call various things like TF handler and handle encoder. So that's actually which version of BERT that we are using. Pooled output shape. So pooled outputs are actually in the form of vectors that BERT gives as an output. From those vectors, we can make any classification. I'll show you as we go along. Output values. So these are actually the tensors that we receive, tensors or vectors. Sequence output shape. So actually it has sequential outputs as well. Sequential outputs and sequential output values. For this example, we will only go with these pooled outputs. These are pooled outputs. These are just vectors, simple vectors. If you want to go with sequential outputs, if you want to use sequential outputs, you can use that LSTM layer or RNN layer. So let me move forward. We create a model. We finally are now creating our
So
model.
can we go back a bit? Can you just highlight some difference between pooled output and a sequential output?
If you see here, pooled output is just this part. We have only fetched 12 IDs from the pooled output. We have a vector of dimension 512. We only took 12 out of those. So this kind of tensor, for us, it is meaningless. The pooled output, after it goes through those Keras layers, that would make sense. Right now, these are just normal vectors for us.
So
And
this
if
is
you
the
want to
vector
see the
for that
sequence,
sentence, right? Pooled output for 512 dimension 0. For 512 or one row, it is a vector for that sentence, right?
Yeah. Yes, sir.
Okay, just like word to vec.
Yeah. And sequence output. So these are sequences. So if you see here, we have a 128 by 512. We have 128 sequences, and all those sequences are of length 512.
What is meant by sequences here? Yeah, why there are 128 sequences?
Sir, it has created sequences by itself. So sequences, if you remember, while we were doing bidirectional LSTM, we used to give 3D tensors, number of the length of sequence, the dimension of each sequence, and there were 2D sequences, right?
Yeah, okay.
So those kind of sequences, which means we have multiple vectors for the same statement.
But why multiple vectors for the same statement?
So that's a sequence, no? Because you have to see the previous for the previous word as well. Then you go for one sequence for previous word. For each word, there is a shifted sequence, no?
Okay, someone will take it offline, so I think so we can go ahead. I think how I'm not still clear like how these 128 sequences out of form actually 512 is the size of the vector that I can understand, but how this 128 number came, so that we have to think a bit. So that we can take offline, no problem.
Yeah. So now we come to define our model. So it's a simple Keras. So the same process that we do for Keras model, we add layers against each. We add layers one by one. So first we have this input layer, text input. So just a Keras input layer, and we have defined here that we are giving string inputs. Name column doesn't matter. Name is just for remembering your layers. In case you want to remember your layers, that's why name entity is there. Name is optional parameter. Main here is shape, since string outputs are of variable shape, so we have not provided here. It's string input, so we have specified that whatever the input we are getting is of the form string. Pre-processing layer. So the pre-processing layer we have seen earlier. We call the pre-processing layer, and from that pre-processing layer, we make this encoder input. The encoder inputs would actually take your text input and pass it into pre-processing layer. So if you see a pre-processing layer, and it has gotten the text input. That text input, sorry, not here. Now we have done pre-processing. We need the encoder layer. So this encoder layer, again, we have imported it. Trainable is equals to true, which means we can train the layer. We'll get into how fine tuning is done and all. We'll get into that in later session. So, and outputs. So the encoder we have declared here would actually take the previous encoder inputs. Encoder inputs we from pre-processing layer and passing our input text into that. Input text, So just to give you a flow of how it's happening, we take the text input. Text input goes into pre-processing layer. Pre-processing layer would give the output of pre-processing layer goes into a encoder layer. And from that encoder layer, we take these pooled outputs. So we have seen here, pooled outputs is this vector of dimension 512. We take those outputs. Now, at the end of from those outputs, we to those outputs we add dropout layer. Dropout layer is just for regularization, and we add a dense layer at the end of it. So to our dropout layer, we have connected the dense layers. If you see here, the name of previous layer is added at the end of current layer. So net earlier net was this layer, output layer, but now after since we have added net here, so net would actually output layer, all the layers till here are connected to our dropout layer, and the final dropout layer becomes net. Again, in the next step, dense layer is connected. So net currently has dropout layer, which and dense layer to the end of it, and this whole system is now net. And finally, we call this TF-Keras model. Model would actually do the compilation process. We earlier it is similar to calling .comp. Earlier we have called the .compile method. It is similar to and here we have put activation is equals to none. Activation is equals to none because we are separately using the sigmoid function. Again, if you want to classify via the model itself, you can add sigmoid here. If you have multiple classes, then you'll have to go with softmax.
So where you have used the sigmoid later on? Huh?
Yeah, sigmoid here in this step, no sir. We just take the output and directly add sigmoid. This is done because we are using the pre-trained version as well. Na? So finally, we call this model. So it is equivalent of calling .compile. So we get the model object. We call the function we have declared here to actually get our model. So this classifier model is our model, and we pass our text. The text we have seen earlier, testing text. Let go. Yeah, this is such an amazing movie. We pass this text to our model, and we call the sigmoid function. So since we have not added activation, we get the raw result and call sigmoid on that. We call sigmoid on that result, and we can see we get this kind of output. So currently the output is meaningless for us because it's just a sigmoid value. The dense layers have not been trained, so doesn't actually make much sense. But if you see, since it is a pre-trained model, it has given us output. And if you apply a threshold at this point, you'll get the result as well. If you add some threshold, let's say 0.5, the general threshold that we take for classification, if you take that, we can actually classify it as negative. So obviously you can see the classification is wrong because we have used the positive statement and we are getting negative result. So since we are just using pre-trained model, we can fine tune it as well. So now we'll go into the training process. Training process would actually fine tune the BERT model and adjust the dropout as well. Since dropout layer randomly cancels out couple of weights. So which random weights to cancel? Which random selection would actually give us good results? So for that, so it would actually train these two layers. If we can see the sequential flow of our model, I've already explained, but we'll just go through this diagram. So the text input layer connected to pre-processing layer. Pre-processing, then it goes to encoder. what the pooled output that we the encode pooled outputs that we get from encoder will pass through dropout classifier layer. Since we have already added single dense layer, so no need of training. We can use the pre-trained as well, but we'll go with training now. We create a loss function. Loss function here we have binary cross entropy.
So one question on
Yeah.
this, since it is a pre-trained model,
Hmm. Sir, your voice is not clear. Hello? Hello? Am I audible?
You're audible. I think.
You go ahead, Soman. You go ahead. Actually,
Okay.
he will join later.
Okay. So binary cross entropy, we are using binary cross entropy as our loss function, and matrices, that what a evaluation matrices. So binary accuracy, we'll use those again. And also we need Adam optimizer. So this is actually another version of Adam W. The description is given here. Adam W is actually weight decay type Adam. So for the first few iterations, it would use a lower learning rate and then move to a higher learning rate. That kind of it follows. So here we have epochs, the number of training epochs that we need, steps per epoch. So uh, how many steps how many batches you want to process per epoch. If you do not pass it, all the batches will be used for training in each epoch. So to get steps for epoch, we just call TF data experiment cardinality training numpy. This whole function actually means we are using all the batches. Since instead of calculating the batches ourselves, we are just calling this TensorFlow function to pass the number of batches that we want. So that will give us steps per epoch, number of training steps. So steps for epoch times epoch. So number of training steps would, it's simple by the name itself says, as many steps per epoch we have times number of epochs. And number of warm-up steps. Since we are, since the Adam, as I said, the Adam weight decay actually uses lower learning rate for couple of lower learning rate for first few instances, then goes with a higher learning rate. So for that, we need warm-up steps. So how many samples we need for lower learning rate? So that is number of warm-up steps. So whatever be the number of training steps, 10% of that. So 10% of the training would be done with lower learning rate, and then we'll move to a higher learning rate. That's the process. Initial learning rate. So we have 3 to the power minus 5. 3 into 10 to the power minus 5. That is our initial learning rate. Now we actually create the optimizer, that Adam W. So earlier we have imported this optimization library. So from this optimization library, we call create optimizer. We pass the initial learning rate, our number of training steps, number of warm-up steps, and which optimizer that we are going. So that is Adam W. This will give us our optimizer. We call compile since we are training. So now we have to call the compile. We call optimizer. We pass our loss function and matrices. Loss and matrices we have declared earlier. Binary cross entropy for our loss and binary accuracy for matrices. And then we'll just have to put it through training. So we call the fit method. Fit method actually gives us the history object. So fit method, we pass X data is training data. X data would actually mean it involves class labels as well. So as we have in scikit-learn, we have separate X and Y. It's not that. X data means the whole training set. Training data set, it will automatically take your class labels and your training columns. Validation data set, validation DS, and epochs. If in case you are using through pandas, if in case you are using through pandas and you have separate X and Y columns, then you will have to go with X is equals to this data set, Y is equals to this data set. But since we are using that TensorFlow text dataset object, so we do not need to do that. It takes care for us. We pass training dataset, validation dataset, epochs. We are just running it for 5 epochs, but it actually takes a lot of time to train without without a pro version of Google Colab, without a GPU. It was taking me around 6 to 7 hours for the whole training. After using Google Colab Pro, I was able to do it under 30 minutes. So it's a very heavy training. It takes a lot of time. And also we have huge data set, 20,000 samples. So it takes time to train. And we have just limited the epochs for good results for proper training. I would recommend to go with around 50 epochs, or just set epochs to a high number, say 100 or 100, and use early stopping parameter. So that would give you good results. So after calling this fit method, our training is done. And after training, we get our loss and accuracy. So this actually gives us the history object as well as our classifier model. So we pass the test data set through our classifier model. So we get here loss is 0.4 and accuracy is 0.85. So around 85% accuracy. We have only ran 5 epochs. So that's the reason for less accuracy. If you go with more epochs, it would give you better accuracy. If you want to see the training curves, so we have this plotting code for plotting. So we just take the history object, we take history out of it. History means training history. We create a dictionary, and from that dictionary we can call the keywords accuracies, validation, accuracy. So accuracy for training set, accuracy for validation set, the loss for training set, and the loss for validation set. These just go with these keys: binary accuracy, validation binary accuracy. These keys are not customized. You have to use exactly these keys to get your result. We have epochs, so as many number of epochs that we ran. One to length accuracy. So whatever be the length of accuracy plus one. Since we are starting from one, we need to go up to 6. So because last element is not included in the range function. So in order to get 1 to 5, we go 1 to 6. So length of accuracy plus 1, that would go 1 to 6, which means we'll get 1 to 5. We create a figure. So matplotlib we have imported earlier from as PLT. So plt.figure, that would give us figure. We define the figure size 10 by 6. Tight layout to just manage the borders and padding for your figure. Subplot, since we need actually 2 plots. So this is 2 by 1 subplotting, and the first plot number 1. So plot number 1, we pass the label training loss. We are using color red. R stands for red. If you want, you can pass any that hex code for color, and you can get your color as well. Or you can just use these short notations: R for red, G for green, B for blue. Or you can type out as well, REDBLUE. That would give you colors as well. We pass epochs versus loss. So epochs goes on x-axis, number of epochs, and the loss values go on y-axis. Again, in the same plot, we call validation loss with blue color and label being validation loss. We create the plot out of it. We can define labels separately. So Y label, we have made loss. Again, since we are using subplots, we are making two plots. So again, 2 by 1 subplot and the second number of plot. So in the same plot, it would end up at the second position. Here we pass epochs, accuracy, again the colors and labels, training and validation accuracy. And if we add labels here, so we get epochs versus accuracy and legend. So this will get this kind of result. These are our training losses. So if you see here, there is no convergence so far because we have only few epochs. But if we increase epochs, there is possibility that we'll get better convergence. If we still do not conversion, then we need to tune our model. We need to add more layers or drop out and all that. We need to go through hyperparameter tuning of our model for the dense layers as well. That would give us the result. So we can save our model separately. So in order to save our model, just connect to your drive, or you can save your model on a local path as well. That's up to you. And we'll have to pass the directory. So whatever be the directory, and we add name here. So just IMDb, it will create the name IMDb underscore BERT for our model, and it will save our model at this directory. So I'm saving at on my drive. It will save the model. We have saved. We call the save function or on our model. That would give us the model at this path. Include optimizer false. So whether you want to include optimizer or not, that's up to you. And we can again load the model if you want to use it later on. Just call saved model dot load and again pass the same path. You'll get your model. You can get your model imported, and once we have that, we create the result. Here we'll just couple of examples. So we'll print the examples. Let me go through this part first. We have couple of examples here to test with our model. We have one model at on our machine and one model that we have saved and imported back. These are both same models, so there would be no change in output. So just to display that, we through these examples we pass them into TF constant. TF constant is basically equivalent of creating a NumPy array. The output is equivalent of NumPy array. You can add typecasting function as well. So if you have list you want, if you have list of since here we have strings, so it won't work. But in case you have the list of numbers and numbers are in form of string, so you can either convert numbers into integers or floats, or you can convert floats into strings. So typecasting is also available. The result would be a equivalent of a NumPy array. The object is different. It would be a TensorFlow constant object, but it is the equivalent of a NumPy array. We pass it through our model, and whatever be the output of that classification, it goes through Sigmoid function. So that is available tf.sigmoid. It goes through Sigmoid function, and we get results. So since we are testing the saved model as well as the model available, model instance available at our runtime, so we have reloaded model, original model. We take the result from saved model. We print example. So printing is just simple. It would take your inputs and your results. So whatever input you have and result, it would create a list out of it. So whatever your inputs are and scores. So whatever scores that we get from these results, and it would print them. It would print your results. So we have list here. It would unfold the list. The star operator means all, so it would take all elements from the list. Separation is \n, so they are separated by new line, and we print them. So you see here, this is your output. So this is such an amazing movie. It's a positive review. So 0.999 score. This movie was great 0.998. This one I think is a wrong classification because this movie was meh. It's again 0.95. This is not a negative but almost neutrally review. This movie was okay, so it has a lower score. This movie was terrible. This score is very less. So if you add a threshold, let's say 0.5 threshold, so you can classify them as either positive or negative. Or if you want to go directly with classification, I'd recommend to add the optimizer right at your dense layer. We have added optimizer separately. I'd recommend to add the optimizer while creating your model here, that activation function. Sorry, I was saying optimizer, it's actually activation function. So you add the activation function right in your model. You'll get the result from your model as well. So that was the hands-on example of BERT. Thank you very much. That's all from my side today. If you guys have any questions, the floor is open.
Yes, we'll keep open for a couple of minutes. Sahuji, any question? Shailesh? So once again, a wonderful representation, wonderful presentation by Soman. So thank you,
Sir.
Soman, for a great job. So we're all thankful to you. And any couple of questions we'll take up if anybody has any questions. Otherwise, we'll take up some discussion after this recording. Anybody, any questions? Sahuji, Himanshu, any questions?
Sir, I was actually not very clear. Concept I could not actually understand fully.
Which parts? I'll repeat.
No, not part. Entirely the concept itself, right?
Sir, this is demonstration of the BERT pre-trained model, how to use the pre-trained model. So I've added example of dataset, how to get the
I think
dataset.
maybe I
And
didn't attend last class maybe because of that. I will study
okay.
once more. I noted down the URL.
Yeah, so now I'll give you, Sahuji, the video link so that you can pick up the last class. Yeah, then you will understand it better.
Yeah.
Okay.
Someone, my question is, suppose if the model is already pre-trained, right? So suppose if
Yeah.
I have ANN or regression or any other pre-trained model, then only one line is sufficient, na? Predict and call that model and then give the input,
Pre-trained,
right?
sir. That depends. If you have a pre-trained model like this, like here
Then
I have.
why so much coding? That's what my question is. Because here almost we are redoing overall setting, na? So why is so much this thing, na, for this BERT?
Sir, because we are, excuse me a minute. I'll just get back in a second. Okay, sorry for the interruption. Yeah. If you see here, the model the model that was optimized, that fine-tuned in this lecture was actually saved at directory and then reloaded. So that model we directly use for prediction, right? Here.
No, but what we discussed earlier is
No, I will answer.
Sir, I'm getting to that. That's actually because the pre-trained model that we are talking about are not actually in the form of models, but actually in the form of pre-trained layers, right?
Oh.
They are in the form of layers. So in order to get the output, you'll have to create a model out of it. Now, these are pre-trained layers. You will not train those layers during your training process, but you'll need to add those layers to your model. And again, these layers work within themselves as well, because if you see here, we have just called the layer and passed text through it. So the layer is pre-trained, it worked without even making a model out of it, just by these two statements. Text
again
and
we
pass.
are training it, na? Then at the later stage, we have to
Yeah,
set all the
that
input
is,
and all, na?
yeah, that is for training the model. And in case you are doing fine tuning, then for fine tuning or your additional layers, since we have connected it to ANN, that's why if you want additional, if you want to add additional layers, you'll have to train the additional layers. No, additional layers are not pre-trained. For that, we'll have to go through training process.
Okay. Okay.
Otherwise, you can just use these layers as right here. We have used we have called the pre-processing layer directly from this link and directly passed our text to the pre-processing layer. We get pre-processed outputs. And after passing those pre-processed outputs through the encoder layer, we directly get this kind of output. From that output, you can directly call this sigmoid function.
Oh, okay.
On
Okay,
that
got
layer itself, you can call the sigmoid function, but the result might not be so good. So for that, you'll have to add the layers, model layers. That's the thing.
So those are the layered layers which are pre-trained. In order to build the
Yeah.
model, we have to add subsequent layers.
Yeah.
Okay.
The encoder and preprocessor of BERT that we are using, those are pre-trained. They are already defined, available on those links. We just pre-train the rest of the training process is for rest of the model. And in case you are doing fine tuning, then it would include then it would include training of your layers as well.